Okay, to talk about the cotangent graph and its transformations, I'm going to start with a quick reminder of what the tangent graph looks like. It goes through 0, 0, and it has asymptotes at pi over 2 and negative pi over 2. And actually then, every pi units, it has another asymptote, right? I go pi units to the left of an asymptote or pi units to the right of an asymptote, I get another asymptote. But I'm not interested in tangent here, I'm interested in cotangent. And I wanted to show you before we talk about cotangent what negative tangent looks like. Notice that I can define f of x as something and then just say I want the opposite of f of x. That means it's going to graph now for me negative the tangent of x. So here's negative the tangent of x. And notice that basically what's happening is that for any given x value, let's grab this one here, for any x value, tangent has a positive value and cotangent has the same numerical value, but it's negative. Or if tangent has a negative value, cotangent has the same numerical value, but now it's positive. Okay, and that's different from what we're going to get with cotangent. It's interesting to note, I think what I'll do is hide tangent now and just graph negative tangent and cotangent at the same time, because it's quite an interesting phenomenon. Oop, let me change the color there. I'll make it green. So negative tangent is black, cotangent is green, and it's the same curve, it's just shifted over. So cotangent is a shift of negative tangent. I think that's quite interesting. But now if I graph tangent and cotangent at the same time, hopefully you'll remember that it's not quite as obvious as just flipping it over the x-axis. Where tangent has a 0, the green graph cotangent has an asymptote. And where the orange graph tangent has an asymptote, the green graph has a 0. So that's cotangent. But now I'm going to do the same thing with cotangent as I did with tangent, except that this time I've already spelled out what my function is going to look like. First of all, I've defined the function g of x as the cotangent of x, and then I've defined the function h based on the function g. So this says take the function g, multiply its x by some number b and add c to that, multiply the whole function by a, and add d to the whole function, right? And now if I make my values of a, b, c, and d 1, 1, 0, and 0, I'm saying don't multiply the function, don't multiply the x, don't add anything to the x, and don't add anything to the function. Then I get the same graph for h as I do for cosine. I'm now going to change that one to yellow because I think it's more obvious. If I turn h of x on and off, you're getting exactly the same graph. If I change a, I wanted this to jump by ones rather than, here we go. If I change a to some number other than 1, then it changes the graph. And it does that by stretching it in the same way as tangent or sine or cosine gets stretched when you increase a, or squished, or I guess flipped if you decrease a. The same thing happens with cotangent. B, the value next to the x inside the argument, should introduce additional cycles of cotangent. And sure enough, my orange graph is cotangent. My purple graph is this h of x, which is the cotangent with, because this number is no longer 1, it's got extra copies of the graph in there. All right, put that back to 1. C is what happens when you add something inside the parentheses, and that means we're going to shift to the left or right. Remember, the orange graph is my tangent graph, and the purple graph is my cotangent graph. So that's shifting, and it's shifting by 1. So let's see what happens if we shift by multiples of pi over 12. I bet I can get it to line up exactly with the cotangent graph. Okay. And D is the number here that takes the whole function and shifts it up or down. So once again, the same graph, shifted over, shifted up. That's not what I wanted. Let's move it to the right. Let's make B something like 2 or 3. We don't want too many copies. Let's make A negative. Why not? I've now introduced you to sine, cosine, tangent, and cotangent, and how you can transform those 4 graphs. You can either stretch a sine graph or a cosine graph or a tangent or a cotangent graph. You can squish more cycles of sine, cosine, tangent, or cotangent in by changing A. You can shift the whole thing, sine, cosine, tangent, or cotangent, to the left or the right, or up or down by changing C or D. The same things apply to all four graphs, and they'll apply to secant and cosecant as well. Okay, I started to set up for something else before I realized I hadn't really finished this video. So just on my way out, I want to mention that we've now talked about transformations of tangent and cotangent, which is what this topic, this subsection, is about. In the next video, I'll talk about the transformations of secant and cosecant. And after that, there's not a particular topic in the textbook, but I'm going to do a video that reviews the concepts, not from the perspective of if I tell you what A, B, C, and D are in an expression like this here, can you graph it? Because that's important. But also I want to talk about if I give you a graph, can you find out what the expression is? That's something that isn't given its own topic, but it's an important skill. So for now, we're going to call this one quits. Nice short video. And I'll talk in the next topic about secant and cosecant.